Let's talk about the properties of similar triangles. But before we do that, let's get a little refresher of cross-multiplying, since that can save us some steps in solving with similar triangles. So, if we have ratios that are equal to each other, meaning we have fraction equals fraction, nothing else going on outside. In fact, I'm even going to just do that so we really don't even see anything outside. So, nothing is adding or subtracting on the outside. It's just fraction equals fraction. What we can do is drop the equal sign, or rather bring the equal sign down. And what we're going to do is go across numerator to denominator and numerator to denominator. And on each side of the equation, you're going to take those pairs and multiply them. So on one side, we're going to have 2 times 3. On the other side, we'll have x times 4. So that'll be a 6 equals 4x, divide by 4, and that should be a 3/2. So with that, it just makes some solving a little bit more quick. As compared to, actually, let's go ahead and show this, because when we solved with fractions previously, we talked about using the least common denominator, which is absolutely valid. And here our least common denominator would be 8. So what we would do is multiply both sides by 8, and we'd get some nice cancellations. And what you can see is we end up at that spot right there. We're going to have a 4 times x on one side and a 2 times 3 on the other side. So both ways absolutely work, and you'll get to the same exact answer. So either way. With this one, and again, I'm just going to get that one out of there. So I'm going to go ahead and cross multiply. So I bring the equal sign down. We don't want to lose that. X times 8 equals 3 times 5 is 15. Divide by 8, and we end up with that fraction there. All right, quick little review of cross multiplication. So now let's talk about similar triangles. So what makes similar triangles is if we compare the angles with each other. They have matching angle measurements that line up with each other. So with this one, it would be that angle B is the same measurement as angle E. Angle A is the same measurement as angle D, and angle C is the same measurement as angle F. So what we would do is we would say this triangle ABC is similar to triangle DEF. And just in terms of notation there, so that squiggle here means that it's similar. And notice the order that I went in. So I went A, B, C, and it has to line up that like D matches up with A, so that goes first. E matches up with B, so that goes second. And F matches up with C, so that goes third. So we have similar triangles. This brings through the idea of scaling. Like if you've ever used a photocopier and blew something up to make it bigger or shrunk something down. It's like preserving the overall shape. It's just either shrinking it or blowing it up. And blowing it up as in making it bigger. So with that, there's a ratio at play. There's a scaling going on. And what we'll have is this relationship that if we take the side lengths, so if we take that side length AB, its ratio compared to DE is going to be equivalent to BC compared to EF and CA compared to FD. So what we end up with here is once we know our two triangles are similar, we kind of line them up, and then we can create these ratios of side lengths. So A to B is similar to D to E. Now we can see those are different side lengths, but the ratio of comparing those two will be the same as the other two matching side lengths matched up. And then we could even go and use the other side length because that'll have a common ratio. So the idea is like how we went from this triangle ABC to scale it down to DEF is going to be consistent across all of the side lengths. We just have to be careful that we make sure we get the pairings correct. And then you just want to be consistent that if I have side lengths from ABC in the numerator, then side lengths from DEF need to be in the denominator. We could totally switch this around. We could have done DE divided by AB, but then all of the fractions would have to flip. So it's like all the numerator comes from the same triangle and all the denominator pieces come from the other triangle. Okay, let's see this in practice here. So we want to determine this side length x using properties of similar triangles. So we're assuming these two triangles are similar and they're nicely lined up for us. So what I could see is, I'm just going to kind of color this so I can see the pairs of our side lengths. And up above, we wrote it as a relationship of kind of 3 pairings, but when we're solving, we just need 2. So let's see, I'm going to work with 66 and x together, and yeah, let's go ahead and write it as 66 divided by x is equal to, and then I just want to go in the other direction, and I want to use the side length where I have 2 pieces as well, which is 42 and 35. Okay, then this is why we reviewed cross multiplication, because then I'm going to cross multiply. So I'm going to have 42 times x equals 66 times 35. Oops, typo, times 35, which is 2310. And then we want to divide by 42, which is 55. So that tells me our missing side length there, 55 feet is our missing side length. Let's look at one more example here. So we're going to have our similar triangles here, and we'll assume they're all nicely lined up for us. All right, so I'm going to get y compared to 15. So y divided by 15 is equal to 42 divided by 63. Let's go ahead and cross multiply. So we're going to have 63 times y equals 15 times 42, which is 630. Divide both sides by 63, and that should leave us with 10. So our missing side length there is 10 meters. Okay, so those are our properties of similar triangles. What we're looking for are 2 triangles with all the same angle measurements, and then from there we can create these ratios of side lengths to solve for missing side lengths within the triangle.